Okay, now, another thing that happened to me tonight is that 2 minutes ago, I was told that I had to introduce the speaker. So I just interviewed him. But I've known him for a while, so I can kind of do it. Okay, it's a great pleasure for me tonight to introduce Professor Anders Nilsson. Professor Nilsson works at SSRL, whereas the place where we make all this synchrotron radiation that he will talk to you a little bit about. Professor Nilsson got his PhD at the University of Uppsala. He's from Sweden. He's been at SLAC for 9 years, but he's still a guest professor at the University of Stockholm, and he travels back and forth all the time. You're lucky to get him tonight. When are you leaving? Anyway, next Saturday he's going the other way. His specialty is fundamental research using synchrotron radiation. He particularly works on problems that they just talked about at the State of the Union speech, so you have a hard time to follow that speech, and energy and environment. He's an experimentalist, and he works with X-rays, and one of his main interests is the chemical bond, the thing that keeps molecules together. Sometimes they separate. Sometimes they marry, sometimes they divorce, right? But that's the bond, right? Yes. So he's going to explain to you, by the way, I hope you all wash your hands tonight with water, because he's going to tell you what happens when you do that. So you have the title there, Water, the Strangest Liquid. Anders, it's your
Thank
turn.
you, Herbert.
Okay.
Thank you. So can you all hear me?
Your phones.
Yes, please, turn off your phones. So it's a pleasure for me to be here today, and also it's a pleasure to see all of you here today. And I hope you will go out of here actually and really understanding a little bit more about this miracle liquid I'm going to talk about that I call here in the title. It's a really strange liquid. But I hope at the end here you will actually see that it's not strange, it's actually rather special in its special properties. Could we turn down the light a little bit? So what I'm going to describe is actually how we can understand. That's too much. So what I will describe is actually how we can understand these rather strange properties of water. What I mean with strange is that they are unusual and different from most other liquids, most other chemical compounds, how we can understand it in terms of the molecular structure. And I will try to keep this on the level that most of you should actually be able, whether you have a scientific background or not, be able to understand, and you're most welcome to ask questions about it afterwards. So let's introduce water a little bit, and why is water important for us? And I think this is a picture that most of you have seen before. It's the blue planet. It's actually the picture from Apollo 11 from space taken towards the planet Earth. And as you can see, the planet Earth is a blue planet. And it is blue because we have all water, so much water on Earth. And everything we do here on Earth has to do with water. It's the key chemical compound for our existence. We know that each human being is probably of the order of between 60 to 90% actually contain water. A newborn baby has, has something happened here. I have to give a public lecture now. That was a good reminder. So we are all made of water, and it's interesting in a way when people actually are looking at life from other planets, or thinking if there could be other life forms out in the universe, they actually first look if there could be water, and particular water in its liquid phase, not in like ice or in the gas phase, but in the liquid phase. So water is something very, very special, and it's the basis of actually why we are here and we actually exist here as a human form. It's of course unique for all biological life, not only we as humans. It's also unique for plants, animals, everything. And it's also pretty much involved in controlling our climate, involved in erosion, weather, everything has to do with water. First, also, I like to show that we also actually have some appreciation of water. I just show this beautiful waterfall here at the border between Argentina and Brazil. And here's another picture here in California of Lake Tahoe. And there is another aspect of water that I think we all appreciate in a way. We are all drawn to water. Water is beautiful for us. We like often to relax, taking a bath, and I myself personally, I'm very drawn to water. I try to go a couple of times per year. I actually go and swim with dolphins in Hawaii. I love to be out there playing with them in the water. So we actually, in a way, are finding water something very special and unique to us. So there are other issues with water. This is a picture I took from Al Gore's movie, Inconvenient Truth, that I'm sure many of you have seen. And something that is a little bit, let's say, uncomfortable or scary for us for the future is whether we will have access to clean water. So with the climate change, water, the access of water will be one of the major challenges with respect to the climate change. However, water could actually be also part of the solution. So here's a picture of, we might actually make energy out of using sunlight and water. And here's a quote from Jules Verne, who was a very famous French author in the 19th century. He wrote maybe one of the first science fiction author, and he said that, "I believe that water will one day be employed as fuel." And as he ended this, water will be the coal of the future. So this is a picture, which actually demonstrates how we can use sunlight together with water. And the sunlight, the energy that comes from the sun, will then split water into hydrogen and oxygen. And we will then use the hydrogen as a storage. We will store hydrogen in our car, for instance, if we use this for the transportation as a fuel. And then we actually will put the hydrogen into the fuel cell and combine it again with oxygen to make water. And then the energy is released that we put in from the sun. And then we actually, in that sense, we can drive the car on the energy coming from the sun. So the water will quite a lot of research attention now, and maybe we will have something like that to come in a decade or two, if this is really going to work. So this could be a future really development of using water also for our energy purposes. But the focus today is really to talk about why water is weird or strange. Everybody knows that water is H2O, but what is it, something special about this H2O? And I'm going to describe a couple of properties that water has, which is quite unusual. And the first one here, it shows an iceberg floating in the ocean. And this is, as I show here as a title, water is denser than ice. It means that the liquid has a higher density than the solid. Nearly all other chemical compounds is the other way around. As you freeze something, it shrinks, it becomes smaller. Here is the opposite. As you actually freeze, it expands. Many of you probably have that experience, which I had as a kid or even as a teenager, where you try to cool a soda or a beer in your freezer and you put it in there, you forgot about it. And it all actually, the glass exploded. And it's because then the ice actually expanded when it froze into ice. So this is a very, very strange property. Normal liquid, I took as a few examples here, like alcohol, gasoline, or anything, behaves the other way around. That when you freeze it, it shrinks. This is an interesting property also because it actually shows the possibility for how life could evolve on planet Earth. This is one part of the key, because as water freezes, it will float on the ocean. And it will in this way form actually an insulating layer. If water would instead freeze where the ice would have higher density, it will freeze from bottom up. Most likely, marine life could have not evolved in the oceans if that would actually be the property, that we will actually freeze the ocean bottom up. Another unusual property is the density maximum. It's a little bit more subtle in a way, maybe to see for you. I don't know how many have actually done this little experiment. If you take a glass of ice water and you put a thermometer in it, and then you measure the temperature of water at the bottom of the glass, you're going to find that it's actually always going to be 4 degrees Celsius. And why is that 4 degrees Celsius? It has to do with that we have what's called a density maximum, that the water at 4 degrees has the highest density. So here is a plot. So one of this diagram I'm going to show. So on this axis I show temperature in centigrade, and here's density. And we see very small variation in density. This line here shows a normal liquid, which could be like gasoline or alcohol or ether or any other type of liquid. And as you can see, as you cool the liquid, the density goes up. And you can understand that very simply by, as you cool something, things doesn't move around on the atomic level so much and therefore becomes small, shrinks, the volume gets smaller and smaller. But look at water. Actually, it behaves like a normal liquid in the beginning here, but then it starts to deviate. And then at one point we reach a maximum, and that maximum is at 4 degrees. And then it actually starts to go down. As you can see here, it's even plotted that you can look at water below freezing, and its very special property also water has is that you can supercool it. You can actually cool it below freezing without actually it's forming an ice or crystal. You just have to have very clean conditions to do that. But that's not the important point. It is this density maximum. So if you start now, think that we have ice. So ice has a lower density. We melt ice into liquid water. The density goes up, so the whole thing shrinks. So now after the melting point at 0 degrees Celsius, we continue to heat the water, and it continues to shrink up to this density maximum. Very, very strange. So why is this important in a way? So also, as I talked about the ocean, it means that the water at 4 degrees is the water that is most heavy because it has the highest density. It will always sink down in the ocean to the bottom. Exactly what you see here in the glass, that we have 4 degrees at the bottom. The consequences of that is that it's very difficult to freeze a lake or ocean all the way through, because as you will generate colder water, it will rise up. It will always stay 4 degrees below. So as Earth has gone through many different climate changes, we have had ice times and so on where we had very cool weather. Still, during this time, we didn't freeze the ocean all the way through. Of course, you did that most likely up in the poles, but there were always going to be water where we didn't do that, or that didn't happen. And that allowed marine life to evolve, which eventually led to us. Very, very special property of water behaving like this. Another one, which maybe is a little bit more difficult to understand, but let me explain. Water has a very high heat capacity. So what does heat capacity mean? It's the amount of heat we need to add to raise the temperature 1 degree. So in order to therefore raise the temperature of water, we have to put a lot of heat, or the same, to lower the temperature, we have to take out a lot of heat. So water in this way can store a lot of heat. It is a good heat reservoir. It stabilizes the temperatures in the oceans around the world, because it will require a lot of heat or taking away heat to lower the temperature. And this is actually the reason for that the oceans are stabilizing the climate on Earth. So here I just show a picture of the Gulf Stream. Here is Sweden, where I come from. And without the Gulf Stream, Sweden would probably be like Siberia. It would be extremely cold and not very comfortable to live there. The reason why we can have a rather nice climate in Europe is because we have the Gulf Stream. And that brings water that has been heated up down in the Caribbean and then by the current transported up to Europe. And it's this heat reservoir which is then caused by the high heat capacity of water that allows that to happen. So the ocean currents stabilize the climate on Earth, and which is related to the high heat capacity of water. Another interesting property, high surface tension. Water is the liquid with the highest surface tension. So what is surface tension? Here are beautiful pictures of water droplets, and I'm sure all of you have seen this, how water really forms beautiful droplets. And they form a sphere because it tries to minimize the surface area, and the minimum surface area you can have is by forming a sphere. And that is because of this high surface tension. Of course, that allows a lot of water droplets to form, like in clouds, important for our weather and in many other circumstances. Another beautiful aspect of that, of the high surface tension, is that spiders can actually walk on water. I'm sure many of you have seen this. And an experiment you can do, maybe not with a spider, because we should be precious even with spiders, although I'm afraid of spiders myself, but I love the water, and we share that in common with the spider. But nevertheless, if you just put a little bit of soap in water, or you will see that actually the spider will sink, because then we have lowered the surface tension of the water. You can actually do this experiment yourself, putting a razor blade on the water. It will stay there because of the high surface tension. One droplet of soap, the razor blade will sink. So very high surface tension, unique for water. If you can just take a little bit of oil in your kitchen, and you can actually make some droplets, and you put it out in your sink or on your kitchen table, and you are not going to see a beautiful droplet form as you do with water. Another aspect of the high surface tension is the formation of capillary forces. So it works in this way. So this is like a capillary. It can be a straw or a fiber or some sort of channel here that is formed. And the water has some sort of adhesion here to the wall of this capillary. And that pulls up the water a little bit. And at the same time also we have the surface tension here that actually continue to pull this up. So many have seen this. As we make the diameter of the straw or the fiber smaller and smaller, the rise in the water level goes up. And this is the result of the high surface tension and the capillary forces. So why is this important? It's because this is actually how plants can take up water. We can drink water very nicely, which I do here now. But plants take up water via these capillary forces. And here's a picture of a redwood tree that we have here in California. And actually the water is transported through capillary forces up in this tree with tiny, tiny fibers. So without this high surface tension of water, we wouldn't have any plants. If water would be like a normal liquid, we wouldn't have any plants. So let's now come to maybe the most unusual property, but maybe also the most obvious to all of you, which has to do with the boiling point of water. So here's going to be a little bit complicated diagram that I will try to explain here. So here we have the periodic table of the elements. I'm now only showing the left part of it. And here I have a diagram where I show the boiling point for different liquids depending on the molecular mass. And I indicated here with a dotted line where we have room temperature. So let's see now, if we take the first look at the chemical group in the periodic table, In this case, we're looking at the group containing carbon. And these elements can bind, make 4 bonds and bind 4 hydrogen atoms, each of them. And what you see now in this plot, as we go from an element with higher mass to a lower mass, as you see plotted here, the boiling point actually decreases all the way down to methane. And most of you know methane is like natural gas. It's of course a gas, and it has a very, very low boiling point, around minus 160 degrees Celsius. So if you now make the similar comparison among the elements in the group containing oxygen, where we will then form water, we will see the same trend as we make decreases the molecular mass, the boiling point goes down. And here we have hydrogen sulfide, and then the next element with the lighter element is then oxygen, and we would therefore expect water to be there. If water would have a boiling point of around minus 80 degrees Celsius, it would be a gas. But we all know that the boiling point of water is at 100 degrees Celsius. So we can have a liquid. So something really strange is happening here. And this is really the first key aspect of water, the mystery of water, that what is really causing this big change in the boiling point. Water should really be down here. So let me now first explain that a little bit. And we will start by actually looking at the water molecule itself. So we all know water is H2O, and it looks like this. Oxygen in the middle with 2 hydrogen atoms, and we have a sort of an angle here of around 108 degrees. We can make different pictures of the water molecule. Many people have seen this as they go to their chemistry lab, and they make these sticks or balls of water molecule. In reality, this is how a water molecule actually looks like. So it's nearly spherical. It's because the oxygen atom is so much larger than the hydrogen atom. It's like the hydrogen atom is a little bit of horns here on the oxygen atom. So this is how actually a water molecule looks like. And how big is it? The diameter is around 3 angstrom. Angstrom is a unit that we use in the atomic world a lot. And I've written down here what that corresponds to in meter. So it's a dot followed by 9 zeros and then a 3. So that's how small a water molecule is in its diameter. So what makes now water to not be a gas at room temperature? And it has to do with some very special bond called the hydrogen bond. So let's explain a little bit what is a hydrogen bond. Here again is the water molecule. Forget about these 2 lobes. Just look at the water molecule here. And you probably all know that there are electrons in atoms. And the electrons are the ones that form chemical bonds. In this case, the chemical bond between the oxygen atom and the hydrogen atom. But now some atoms are a little bit more greedy. They want to have all the electrons for themselves. And oxygen atoms really want to have all the electrons for itself. So it pushes the electrons towards it, and making actually, in that sense, the oxygen atom slightly negative, slightly charged. And since it's taking then the electrons from the hydrogen atoms, it's making them slightly positive charged. So we are getting negative oxygen atoms and positive hydrogen atoms. And that allows now to form a very special bond, where a positive hydrogen atom in one molecule can approach the negative oxygen atom on another molecule. And they have opposite charges here, as you can see. And they are forming a hydrogen bond through this electrostatic interaction. And you can see that the distance here between that hydrogen atom and oxygen atom is nearly twice the distance as you have internally in the chemical bond inside the water molecule. You can make a very simple cartoon in this way. So I will explain that these negative aspects on this oxygen atom actually are a little bit like protrusion of something of the charge sticking out in two different directions, like this. So the hydrogen atoms here are like the arms on this little guy here, and these protrusions are like the feet. And a neighboring molecule arm can then attach to the feet, forming these hydrogen bonds. The hydrogen bonds are actually quite a fascinating topic by itself, because they are rather weak. They are much weaker than what you have the chemical bonds here, or the chemical bonds making a table or anything here in this room, very solid. So they are much weaker than that, but they are strong enough that we actually can form bonds at room temperature in our normal condition, how we sort of live our lives. And this is important also for biology. So you probably all know about the DNA, which has this double helix. The two helix are actually forced together with hydrogen bonds. And that's why they also can easily separate and form. Proteins are folded in many different ways, also through the hydrogen bonds. So hydrogen bonds, I sometimes call it the software in nature that makes nature to come alive. We can change things, we can form things. So that's the uniqueness of hydrogen bond. So let's take a little bit more look of what we call tetrahedral coordination. I will explain that in a minute, because we have these two protrusions here of oxygen charge sticking out of the water molecule on the oxygen side, and then we have these two hydrogen atoms. So we can form a very, very stable configuration in this way. So if you look here, we have this central water molecule here in the center, and each hydrogen atom comes through a hydrogen bond to another water molecule. And on the oxygen side, we have these two protrusions here, where another water molecule could bond via its hydrogen atom going in. And we call this a tetrahedral arrangement. And it's because if you look here, we have a tetrahedron, and in the middle we have a water molecule, and at each corner there will be another molecule. So making a very simple cartoon again with these little guys, you can see here how the hydrogen atoms forming the hands can grab to the feet of the neighboring water molecules on the oxygen side, and on the oxygen side of that guy, it can sort of allow other water molecules' hand to grab its feet. So we are forming a very, very stable configuration where each water molecule could actually coordinate to four others. And we call this tetrahedral coordination. And it's going to be important because this is the building block how we actually form ice. This is the molecular arrangement in ice. Here's again the center water molecule in this tetrahedron, bonded to four nearest neighbor. If you now started to add more water molecule around this, you're actually going to form something we call hexagonal eyes. And this is just how we added more and more water molecules, and eventually it's going to form a lattice, a crystal of eyes looking like this. One thing I want you to note already now in this crystal is that there looks to be a lot of open space in the middle here. You see it's rings formed, and there is open space in the middle. So in that sense, water in ice is not very compact arranged. And you already can maybe tell now that there's something unusual with ice in that sense, because ice might not have a very high density because of this arrangement. But I'm going to come back to this later on. So now is the question, what is water? So now I describe how the hydrogen bonds are in ice, where you can form it with four nearest neighbor, but how is it in the liquid phase? And now we're going to discuss that. And before I go into that, I'd like to make a little bit of a personal point here, that I want to talk a little bit about my own research. And it's interesting sometimes how you as a scientist can stumble over something. When I started to work on water 10 years ago, I actually assumed that we understood water perfectly well. It must be, it's such a common thing, and we must really understand water. And I didn't expect anything unusual. And I didn't intend to study water either. I was actually going to look at amino acid, the most simple amino acid, glycine, which I've been studying on the surface. This is another my research topic. And I was just going to study it inside water. And we did spectroscopy, which I will describe in a minute what it is. And in order to understand the details of the glycine, I needed to take a background spectrum of water. So we measured water, and when I saw the data, I was so puzzled. I couldn't understand what we saw, because it didn't fit with the textbook of water that I have learned in chemistry and in physics and so on as I grew up in my scientific career. It looked so strange. It didn't fit. And this caught my attention then, and not only me, also we formed a big team, and we have many people working on this since then, trying to unravel why this was different. And this actually led now to a development of another picture of water that I'm going to show to you. And I also wanted to say that this picture is not established or accepted by everybody, although it's in line with a lot of speculation or theories that people have had in the past. But it's a controversial issue, and it's even been written about this debate that we partly initiated in the newspaper here in the Bay Area, because Stanford and Berkeley has opposite opinion about this, and they've written about it like a football game, which is a little bit funny, that we have some sort of match going on here. So let's now, I'm going to describe to you a little bit what are the tools I have used to look at water. And I'm specialist in using X-rays. And what is X-rays? So here's just showing the different, let's say, part of what we call the spectrum of electromagnetic radiation. And we define something called the wavelengths. So electromagnetic radiation are waves, and the wavelength is simply the distance between two valleys or the distance between two peaks. So for you to just have a feeling about the wavelengths of X-rays, we have to put it in a comparison where we are with the visible light. And here is the size of the wavelength. So here's visible light. It's sort of, the wavelength is the order of somewhere between a cell and a virus particle. You can make the wavelengths longer by going in this direction. You make radio waves, etc., where we have a wavelength even of the size of a house. Or we can make the wavelengths shorter, going into the ultraviolet, and then eventually into the X-ray region. As you can see here, the wavelengths in the X-ray region is matching the size of an atom. And that makes X-rays so interesting to use, because we can in that way actually look into matter and understand what the atomic world is doing. Many of you probably are familiar with X-rays, that you actually go to your medical doctor or getting an X-ray, or your dentist. That is more an image of using the X-ray. But here we are talking more using the X-ray to do something magical inside the atom, to learn something about nature and what the atoms are doing in nature. So let me explain one experiment that we have been doing. And this is a very simple picture of an atom. It's oversimplified, and many physicists will say, oh, this is, it doesn't look like this. But let's stay with this very, very simple picture of an atom. And here we have a nucleus in the middle, and then we have electrons that goes around these atoms. And here I'm going to distinguish between two types of electrons. We have what I call the inner electrons, and these electrons are deep inside the atoms, and they are really just around the nucleus like this, deep inside. And these electrons are only on this particular atom. And then we have outer electrons, which are in the periphery here of the atom. And these are the electrons that are involved forming chemical bonds. And these electrons can be shared with other atoms in forming the chemical bond. So we are going to now do some interesting excitations where we are changing these electrons. And we're doing it with an incoming X-ray pulse that comes in here. And it's going to attack this inner electron and actually shoot it away like this. So the X-ray was destroyed, giving its energy to that electron, and it was shooting away. So let's go back here so we do this again. Here comes the X-ray in. We are shooting away this inner electron. And now the outer electron feels there is a vacancy, it's a hole, and it drops down and an emission of a light, emission of another X-ray photon that goes out. And it's really that process, in particular I'm going to show you how this outer electron falls into that inner electron vacancy with the emission of light that we're actually going to look in our experiment. And now I'm going to show you some real experimental data that are going to address the water problem. Just interesting enough, just when I was standing here, one of my co-workers came in with a new diagram of some exciting things of water. So this is something that is still progressing. So let me show you now an X-ray spectra of water molecule. So we have this process now, how an outer electron falls into an inner electron, and we get emission of light. And here we are plotting the energy of that light in photon energy in the diagram here. And then I'm showing two spectra, one from a gas phase molecule. And what you can see is that you see only one single peak here from this particular X-ray transition of the gas phase molecule. And then we do the same thing for eyes, where we are looking now of a water molecule that is bonded to four others in this tetrahedron, in this tetrahedral arrangement. And then you also get a rather broad spectrum, but mainly one peak here. And as you can see, there is a shift between this one and that one's energy position here. So this is with no hydrogen bonding, and this is where we have a maximum hydrogen bonding because we have four nearest neighbors. This looks like the shift is with increasing hydrogen bonding. So if we now took a measurement of water, what would we expect to see if we did this now for water? So I just made a hypothetical spectrum here. So what I took is actually what I call a traditional picture of what most people think about water, which is a little bit like you take eyes and you make it very disordered. You move a little bit of the bonds, bend some bonds, change a little bit distance and so on, and you make it disordered. But it's still rather homogeneous. Most of the water molecules are still in a rather similar chemical surrounding, but there is a distribution of that surrounding which is reflecting in the peak. And you see that position of this is in between the eyes and the gas phase, because we expect that the hydrogen bonding in water should be a little bit weaker than ice, because liquid is flowing, it's easier to moving around than in the ice. So this is what we expected. So when we did the experiment, what do we see? Do we see that? No. What we see is two peaks. That was quite surprising. So two peaks, what does that mean? Could it be two different types of water molecules then in the liquid? And if you look at it, one of the peaks is very close to the gas phase and the other peak is close to ice. It looks like water contains two types of molecules. What could that be? Here I just put up a picture what we could think about it. So this peak, I just draw in this way now with coordination with four neighbors here, similar to ice, as you can see here, because the position is not too far away from ice. Whereas this peak is closer to gas phase, so it must contain a lot of hydrogen bonds that are missing or distorted in a way. So we have to have two rather different types of water molecules in here, in the very different surrounding. I call it very distorted, this structure, and here strongly ice-like. Two different types of structure, mysterious. Why do we have two different types of structures? Why would water choose to do that? And it actually has to do with a balance of two different types of interactions that is causing that. One is maximizing the bond strength. I showed you that ice like to form four bonds, So if we cool water down, it freezes. It should be the most stable configuration. It's when we make the best use of our ability to form chemical bonds. So maximum bond strength. And this guy here, which is much more distorted and lacks some hydrogen bonds, it has to do something with a high entropy. And I'm sure many of you have heard the word entropy, which for me, I remember when I studied chemistry at the university, and I could never really understand entropy. It took me many years to understand what that really means. And I'm not sure I still understand it. It's a really strange term, entropy. So let me explain a little bit what is entropy and how that comes into the picture. It has to do with that we actually often make disorder in a system. We always go to more and more disorder. Formally, it's more related to in how many different ways we can dissipate our energy. But in a simple picture, it can be like that. Let's say we have a room, and we could put out a couple of atoms in a very regular form here in a corner of the room. Let's say like in a gas phase. And then as time will go by, it will actually, these gas molecules will of course then diffuse out and fill the whole room. And this situation is much more disordered, as you can see, than this situation here. We cannot usually go back from such a situation in a room filled with gas. Automatically, it's not going to be that all the gas suddenly accumulate in one corner of the room. So this actually has a higher entropy than this situation. Here's another picture where we make a pile of bricks and we order it very nicely together. And then we could instead make something very disordered. And so this will be a higher entropy than this one. And entropy becomes more important as we increase the temperature as an interaction in nature, which is why a crystal can melt into liquid with high entropy, and the liquid eventually can be a gas phase, which even go to the gas phase, which even then have a higher entropy. So as we increase the temperature, we get more entropy. And this is what is causing a balance between maximizing bond or maximizing entropy. And in water, nature is choosing to do that balance by actually giving rise to two different types of species. It can be looking a little bit like this. So here I show a little bit of tentative motion of water molecules, which could be inside the liquid. So if you look at this guy here, which is having these four nearest neighbor around it, the water molecule is very locked in. It has a problem to really move around because it's sitting with hydrogen bonds of this hydrogen atom to that water molecule and with this hydrogen atom with that water molecule. Can make very strong bonds, but cannot move very much, cannot disorder very much. Look at this guy instead, that has less strong hydrogen bonds, and it now can actually move around much freely in the liquid. And that gives it rise to having a higher entropy. So we see these two type of structures in the liquid. Question is now, how are these structures distributed in the liquid? Are these going to be as molecular fragments sitting next to each other? Or are they actually going to be separated on some sort of length scale? That's the next question we asked ourselves. How could really this look like? And then we took one of the other tools that you can use with X-rays. I show you before what I called spectroscopy, where we lift electrons to different electronic levels. But we can also do what's called scattering of X-ray. It means the X-ray comes in towards your sample and then it's deflected in different angles. We call that scattering. And that type of interaction is more based on diffraction and interference. And I'm sure some of you at least have heard that word of diffraction interference. But let me explain how we do this type of experiment. It's called small angle X-ray scattering. We have our sample, and we have an incident beam of X-rays going through our sample. And then we have a detector here that we can detect the X-ray coming through. So the direct beam, which do not scatter, will of course go straight through without an hitting detector. But there could be some X-ray that will actually undergo some scattering here. And this scattering is in a very, very small angle. That's why it's called small angle scattering. You have often the word diffraction, where you actually determine atomic position. I'm sure some of you know that, but that's going to be a very big angle, very large angle, where the X-ray goes out in this direction. So what this can do with this very small angle scattering is that if you have, let's say, some sort of particle or density difference, so let's say your sample contains some sort of patches or structures here which have a slightly different density than the surrounding. And what I mean with density, you can just think about atomic density in a very simple way. So if that would be the situation, you can actually imagine that we will have a scattering event of these X-rays, but they will be slightly deflected. And this part of the X-ray beam will actually, in the deflection, have a little bit different path lengths than this part of the X-ray beam. And if this path length is of the same order as the wavelengths of your radiation of the X-ray, you can get then what we call interference, constructive or destructive interference. I'm not going to spend time to explain that in detail, but that's how you can get the contrast in your experiment. So here is how an experimental data could look like. And down here we have what's called momentum transfer, but you can just think about very simply in angle. And I plotted now the scattered intensity here. And if we now consider that we will have a homogeneous water, as I just showed you before with this X-ray spectroscopy, where most water molecules are in a very similar surrounding, that's a little bit disordered, broken hydrogen bonds here and there. This is the scattering pattern you will actually expect. It just comes from a peak here, which goes very high up here, which has to do with the scattering from the nearest neighbor, oxygen-oxygen scattering. And it's just decaying from that scattering. So nothing is really happening. And when we did this experiment here at the light source that we hear on site at SLAC, we saw something like this. So when we measure now real water, we actually suddenly saw this enhancement here at very low angles. And that enhancement told us that there are density differences in the liquid. Something looking like this. And the minimum here, in a very simple picture, the minimum and the shape of this gives us the size of these regions which has a different density. And we could estimate that to be of the order of 10 to 20 angstrom. Actually, it's a unit, a Swedish unit, angstrom. He was actually one of the first to describe how you could look at all the different colors, let's say, of light, of white light and so on. So he dispersed radiation. He's from the university where I made my PhD. That's why I know this very well. Anyway, the angstrom unit I showed you before, the diameter of a water molecule is a 3 angstrom. So you could have a sense how big this size is. And it could be maybe containing 50 to 100 water molecules in here. So we have some sort of distribution in the liquid how these two different types of structure will be arranged. And this is maybe a cartoon. We don't know the exact arrangement of this, but we can envision that a cartoon a little bit like this. I showed you we have something that is very ice-like, and then we had something which is very disordered. And this is the one that has this high entropy, where the water molecules are moving around much freely than in the ice, where they are instead much more strongly bound and maximizing the bond energy. And so this is corresponding to a blue region, and this is corresponding to a red region. So we somehow have accumulated these type of structures. They like to hang out together. And these structures also like to hang out together. So we have some sort of mixture of regions of these different structures. In reality, these are actually going to be fluctuations. So these are not going to be stable. They're going to oscillate back and forth. So this region might dissolve into that one, and this region might pop up somewhere here. So it's going to be a dynamic, something is really oscillating around there. To describe it, let's make a very simple picture here. Let's go dancing. Oh, sorry. Let's go dancing. And I'm going to make an analogy here that we are going to a dance restaurant. In this dance restaurant, we have tables here where people sit around and they socially interact. They actually like to get together. They like to hang out together. So they form strong bonds. They like to sit there. And around the tables are people dancing around. Maybe not couples, but more, let's say, like a disco dance. You're really dancing around here. People are moving around fast. Sometimes they hook up with someone else, dancing close together, forming a little temporary bond. Or they are maybe hanging up, many of them together temporarily, and then moving around here in a very rapid movement. So this is then this disordered phase, or not phase, sorry, disordered structure, where we actually have this high entropy. We are disordered, we are moving around. And here we are forming these ice-like structures around here, where people are connecting and hooking up together instead, and socially networking and talking. But we also have some people that are sitting on this table and seeing the excitement on the dance floor and is getting a little bit bored and say, I want to go up dancing too. So he will leave, or she will leave, and someone who has been dancing for a long time is getting tired and take its place instead. So we will have an exchange of molecules that is in this type of structure, where we are sort of more bonded together, with the one who are actually are dancing and are jumping around and have a lot of thermal excitement in the room. And as you have seen here, indicated that the table makes structures which have a lower density because it takes more space, whereas these ones that is jumping around in this disordered fashion can pack together. We can make a very crowded dance floor. I'm sure some of you have experienced this, where you're dancing so close to each other. So you can really pack things together when you're here on the dance floor. So let's see what can happen if we change the temperature. We do cooling. So here we are again, the same picture, jumping around here. What happens now if we actually change the temperature? Since this is a very excited, thermally excited, where we put in temperature that causes entropy to go up in the system, and this is the type of structure you will have if you will freeze the system, where this structure will then, of course, be the whole system. So if you lower the temperature, you're going to form, it's like we are creating more tables. People are a little bit less excited, maybe the evening is long and get tired, they will fold up more tables, more people can sit around. So we will have a conversion as we change the temperature, as we lower the temperature. We will generate more structures where people are connected, calm, peaceful, sitting there. And so as we lower the temperature, the bond energy in the ice-like component becomes more important. And we convert the disordered structure to the ice-like structure. So this is the picture, in a way, of the uniqueness or magical part of water. A normal liquid, like gasoline or alcohol and so on, would not have two structures, will only have one type of structure in the liquid phase. Water is unique to forming these two. And now we'll go back and talk a little bit about these very special properties that water has. How can we understand that now, what I've just showed you? So let's take the first one, water denser than the solid here. Here we have ice, and I showed you before with this tetrahedral bonding, where each water molecule is surrounded by 4 nearest neighbor, it generates a structure which has a lot of open space here. The dominating structure in the liquid, which is this disordered structure, can avoid to have this open space because you can pack the number of molecules much better together, because you don't have so many of these very directional hydrogen bonds. So if you take balls, spheres, and put them together and ask how many can I pack together with spheres, you can actually pack together 12 spheres around a single one. That's what we call a close packing. You can immediately realize now that in ice, each water molecule is surrounded by 4. That's quite far away from 12. You cannot really pack that close together in the ice structure. But in the liquid phase now, when we have this disordered structure, we can do that. We don't need to form this open space. That's why we have a higher density in the water, in the liquid phase compared to the solid phase in ice, where we generate this open space. So we can understand that now, why actually this happened. And of course, most liquid will form more of this 12 nearest neighbor and be a rather compact solid form, and as you melt that solid form into its liquid, you're just going to disorder that type of coordination of 12 around it. So it will behave in that way as a normal liquid. Here, the solid instead, by making these directional bonds, make all this open space. And that's why it has lower density. Let's take the next property, this density maximum. That's a little bit more difficult to directly see. So, again, the water glass with the thermometer, we have 4 degrees of water in the bottom of the glass. And I plotted again the density here as a function of temperature, or the density, how it varies as we change the temperature. Let's go to this picture. Let's identify how this structure and this structure should change its density as a function of temperature. I already said that this type of structure will have a higher density than the ice-like structure here. But we would expect that this type of structure will behave like a normal liquid. So as we cool the system down and we look at only at this type of structure, everybody who's dancing will dance a little bit slower and slower, and they can compact, they can get closer to each other by lowering the temperature. That's why the density goes up. The same with these ice-like structures. As we cool the temperature down, maybe people sitting around the table at higher temperature is a little bit agitated. They are discussing or talking about things and so on. And as you cool it down, they get more and more calmer, maybe eventually falling asleep. And that, of course, makes also the table to contract as you get lower and lower temperature. So that will also vary in this fashion, but it has lower density. That's why the curve is down here in comparison to that one. So what will happen now as we cool the system when we have these 2 components? So if you look at this picture, I only had 3 tables out here. And this picture now we have actually 5 tables. So if I converted some of the dancers into a table. So as we cool the system down, we will then, of course, follow in the beginning this normal behavior of a liquid. But then in this region, when it starts to deviate, it's because we are creating now space here of this structure which has a lower density. And it's that these structures appear in here as a lower density, make this now to change around, and as we cool, the density goes down, although both components should shrink, but we convert the structure which has a higher density into a structure that has a lower density by cooling, by converting this into more of that. That's actually what makes then this density maximum. And many of the properties that you see with water, I haven't shown you all of them, but many of them actually is related directly to the balance between these 2 structures that makes water to be that weird. Just to give you an example of another property, viscosity. What is viscosity? It's in a way how easy something can flow. High viscosity, we can flow it easy. What do you think would happen if you have something that can flow and you put pressure on it? You will compact it somehow, right? You would expect that it doesn't flow so well as you put pressure on it. So what does water do? It doesn't behave as it should, right? So as we put pressure on water, it flows easier. Can we understand that in this picture? Yes. As we put pressure on water, this lower density ice-like is converted into the higher density structure. And the higher density structure has a higher viscosity. You have actually altogether 66 what's called anomalies. Anomalies is something that is behaving differently. 66 of different properties where water behaves different than it should. Let's continue in our list with the high heat capacity. And I'm not going to dwell on that very much, but it has very much to do with this very disordered structure and how water molecule can move around freely, which allows it to give this high heat capacity. Let me spend a little bit more time on this high surface tension, because it's quite interesting in a way that we could form these water droplets, and as I told you, with the high surface tension, try to minimize the surface area by making a sphere. And this has to do with exactly the same property as I show you, that water has a very high boiling point. And remember that, why did water have a high boiling point? Because it can form hydrogen bonds between water molecules like this. So it's the ability for water to form hydrogen bonds that makes it to have a high surface tension. So it makes a lot of bonds between water molecule here at the surface, and if you would increase the surface area, you need to break some of these bonds, and water doesn't like that. You want it to all hold together. How would that be if you take another molecule? I took just some big hydrocarbons, can be gasoline. Gasoline is a liquid because it has a very high molecular mass. So it has a very high molecular mass. It means that it cannot have so much motion around as a small molecule like water can have. And that's why it's formed a liquid at room temperature, gasoline. But the interaction between the water molecules is very, very weak. So it's more, if you look at this diagram with a very heavy element, you could see you could actually have a liquid of H2 polonium. Polonium is a very, very heavy element because it's just heavy. But water is a very light molecule. It's the smallest molecule that we have that exists as a liquid. And it's only that because of these hydrogen bonds. So gasoline is not going to have a high surface tension, or any oil, you cannot form really nice droplets as you can do with water molecules. So this is really the explanation for why we have this surface tension, high surface tension. At the end, I'm coming to my end here, I like to just to emphasize two particular aspects of water that I hope you have seen here in my lecture for you to take home and remember, which is important, what I've talked about. One is the formation of hydrogen bonds that is unique in water, making water not being a gas as it otherwise should be. Of course, this is the number one property that allows us to be here today. Otherwise, we will disintegrate if we would be all a gas inside, right? That would be quite dramatic. Actually, it turns out that the strength of this hydrogen bond at different distances here, if you would tweak that strength just a few %, everything around us, everything we are will change. Exactly how strong that nature of that hydrogen bond is determined a lot of what we see around in our world. The other thing I want you to remember is the dance restaurant. And in particular that we actually see two types of structures in the liquid. And they are somehow separated in space with certain length scale. And maybe this table is actually 50 or 100 people or water molecules sitting around it. And we have something that is bonded together, and they exist because they could really form strong bonds. And they are a little bit like ice-like, but they have a lower density. And then we have this surrounding here, which are these excited water molecules that hops around, and it's like a dancing, forming a disordered high density. And the balance between these two is giving a lot of the magical properties of water, just how I explained for you the density maximum. So, with that, I'd like to end by showing some beautiful pictures here of water, and maybe saying water is maybe not so strange, because maybe we can understand why it behaves like this. But it's very special, and it's unique that it's behaving like this. And before I end, I just wanted to put up a list with a lot of people that has been involved in the work I show you, and funding agency and many different things. So I've not done all this work by myself. And with that, I thank you for your attention, and willing to take questions. Thank you. Let's start with this gentleman over here.
Yes, I have a question regarding organ preservation. Organs are mainly water, like most of us are. And if you could cool them down to below zero without the freezing of the crystallization, could you use high pressure to achieve that?
Oh, that's a tricky question, which is probably outside my level of expertise. But I could imagine that. Oh, so he asked, in a way, if you, for organ preservation, if you, to avoid crystallization, if you could freeze an organ down to rather low temperature by applying pressure to avoid crystallization. As you know, as I said, as we crystallize water, it will expand and it will destroy the cells and so on. And in principle, yes. But as you also put pressure on water, actually the density of the water will go up as well. And you might eventually be able to, I don't know exactly what temperature, but there is a certain temperature, the lowest possible temperature you can reach as you put pressure on before it crystallizes. So yes, I would imagine that you could do that you could actually slow things down. But whatever the pressure itself will actually cause some other disturbance in the system. It's an interesting point, because another strange thing with water is that if you have ice just below the freezing point, and if you think that you have a solid and you apply pressure to a solid, you would think that you would solidify it even more, right? So of course water doesn't do that. As you, yeah, there you have. You could go to I3, but if you have ice just below the freezing point, as you pressurize ice, it melts the water. Actually, that's why we can ice skate, because as you go on the ice, you put pressure as you have ice skates, and you get a very thin layer of water as you skate. Yes.
When you were looking at the X-ray spectroscopy,
yes,
and it looked like room temperature was just about in between where you would expect water's boiling point to be based on all other elements and where it actually is at 100 degrees. So at room temperature, do you think that the high surface tension that exists in water is because of the simultaneous existence of the ice-like structures and gas-like high entropy structures?
So what is your question? If he's asking in a way a little bit of a complicated question, so maybe just summarize the question.
So for the high surface tension that
yes.
exists around room temperature and water, it looks like on the X-ray spectroscopy that was about midway between where you'd expect the boiling point to be and where it actually is, between about
so he's asking in a way if you look at the high surface tension of water, and whether actually the boiling point is in between what you would expect for the gas and ice. I think that's your question. But maybe let me refine this a little bit. The high surface tension, I showed you a little bit now of the water structures in the bulk, where we have these two different types of structures. We actually don't know yet how this looks at the surface. And my guess is that at the surface, we might actually have more of this ice-like, and that's part of it, try to form more hydrogen bonds, and that's why you generate the high surface tension. Let's take another question here.
Yes, what do you think of the talk of Rudolf Steiner and his followers about
before we drink them.
I know that there are many.
Repeat the question.
Yes, I forgot. So Rudolf Steiner is someone who, I think, maybe 50 or 100 years ago, was active to try to do something with water by actually putting it into some sort of swirling fashion into the water, and in that way make water having a more special property. And he mentioned here that we might generate more ice-like configurations. Maybe I should make a general statement that water has caused a lot of people thinking about many exotic topics, like what you just said, and many other topics. And from a scientific point of view, and I only speak as a scientist, there is no way for us today to see any of these speculations of uniqueness of water based on any of such a treatment. We don't have any experimental evidence that actually something is happening with the water when we do any of that. However, having said that, we cannot say either that it's not true. It's just simply we don't know.
There's one question here.
Yes,
If I can ask this question the right way. When you showed the two peaks in the spectrum for
Yes.
liquid water, and then you also indicated at 4 degrees water's most dense, do those spectrum intensities shift as you might expect as the temperature of the liquid water changes?
Yes, they do. So actually, let's see if I can go back to that. Might be a little bit. Let's see if I can do that. I can just show quickly, since this might be a little bit of a detailed question for someone interested in the details. But so here we see these two peaks. Actually, what happens is interesting. As you change the temperature, if you cool it down, I said that we will get more of this ice-like. So what happens is that this structure, this intensity grows and this goes down. So you see the conversion of the disordered structure into this ice-like structure, but that doesn't happen to peak at 4 degrees, no. Because the 4 degrees has the balance of both structure to contract and then converting between them. So it's a balance of that. That makes the maximum at 4 degrees. So I can also just mention for someone who's interested, I talked about this disordered structure that is getting, with increasing temperature, more and more excited and more disordered. And what you see as you increase the temperature, that this actually shifts more towards the gas phase as you go up in temperature.
One last question here.
Okay.
He's been trying for hard.
Yes.
Yeah, I kind of would have expected that the ice-like regions would not get more numerous but larger. And you probably know because of the X-ray scattering angles. Do they get larger as well as more numerous, or just more numerous? Or?
Yeah. So he's asking if the ice, let me go back to this picture so I could, oh sorry, I'm going wrong direction, so we could see what we are talking about. He's asking if these type of structures, let's say the ice-like structure, if they will actually become larger as we change as we lower the temperature. And the answer is yes. We see in let's say what we call ambient water, which is the temperature of water here in the room, around that temperature, they grow a little bit larger, but not very much. However, water can be super cooled, by we mean that we can cool it well below freezing, and there we expect these to be actually start to grow very much larger, much faster than what you see at room temperature. So we would expect them to grow larger, but under these conditions, not much to change in size.
Okay, I think maybe we could stop the big meeting now, and those people who would like to talk to Anders could come down here, or you could go up there and
Yes.
meet them in the hall.
Do we still have cookies and so?
I can't see them from here.
Yes.
So let's
So,
thank the speakers.
thank you.